picture yourself drifting high above the plane of our solar system, looking down at a slow, silent pinwheel of worlds. Before we go any further, if you want a brand new space topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. From this quiet vantage point, you can see the sun at the center, small and steady, a golden lamp around which the planets trace their patient circles. The four inner worlds glide close and warm. The four outer worlds wheel slowly through the cold dark. And between them, in the wide gap that separates the rocky inner solar system from the giants beyond, there is a soft, glittering haze, a faint, scattered ring of stones. This is the asteroid belt. From far away, it looks almost like a delicate band of dust, smudged across the black. Move closer, though, and the haze dissolves into countless individual objects. Some are the size of small mountains. Some are the size of cities. A few are large enough to be called dwarf planets, round and ancient, and lit faintly by the distant sun. Between them lies space, and more space, and more space still. The belt is not the crowded field of tumbling rocks that storybooks sometimes describe. It is a slow, lonely place. If you stood on one asteroid and looked toward the next, you would most likely see only stars. Astronomers think the belt holds somewhere between 1 and 2 million objects larger than a kilometer across, with countless smaller fragments drifting alongside them. Yet, if you gathered every single one and pressed them together into a single body, the result would still be smaller than our moon. The belt is vast in volume and tiny in mass. It is a thin scatter of leftovers, spread across a region hundreds of millions of kilometers wide. And that strange combination, so much room, so little material, is part of what makes it such a quiet puzzle. For more than 2 centuries, people have wondered where these stones came from. The earliest idea was simple and almost poetic. Some thought a planet had once orbited there, between Mars and Jupiter, and that long ago it broke apart. The shattered world in this old picture became the belt. It was a tidy story. It made sense of why the gap between Mars and Jupiter seemed too wide, too empty, too unfinished. But as telescopes improved and spacecraft began to visit these distant stones, the story slowly came apart. The asteroids did not look like fragments of a single world. They looked like many different worlds, each with its own chemistry, its own color, its own past. Some are dark and rich in carbon. Some are pale and stony. Some are dense with metal, as though they once held the heart of something larger. So the question deepened rather than closed. If the belt is not a broken planet, what is it? One leading idea today is that it is a world that never formed at all, a region of the early solar system where the raw material was stirred and scattered before it could ever gather itself into a single body. The suspected stirrer is Jupiter, the great giant just beyond, whose gravity reaches across the gap like a slow tide. But there are other ideas too. Some researchers wonder whether parts of the belt were delivered from elsewhere, pulled inward or outward during a long, complicated dance among the young planets. The evidence is still incomplete. The question remains open. For tonight, simply hold the image in your mind. A vast, soft ring of dark stones, turning slowly in the cold sunlight, far beyond the warm blue of Earth. Each one carries a story older than the planets. Each one is a piece of the original cloud from which our solar system was made. Nothing has been added. Nothing has been finished. They are, in a sense, the leftover ingredients of a recipe that was never quite completed. Over the coming hours, we will drift through this strange and lovely region together. We will visit its largest residence, the round and dignified Ceres, the bright-faced Vesta, the tilted wanderer Pallas. We will sit with the gaps that should not be empty, and the families of stones that travel in quiet groups. We will listen to old theories that no longer fit, and newer ones that may not fit either. And through all of it, we will return again and again to the central question. Why is this ring here? What was meant to happen between Mars and Jupiter? And why, after billions of years, has the gap never been filled? Before we sit with the mystery itself, it helps to know what the asteroid belt actually is. In the simplest terms, it is a wide, thin ring of rocky bodies that orbits the Sun in the gap between Mars and Jupiter. The belt is not crowded. The way pictures sometimes show. It is mostly empty space, with stones drifting through the dark, far apart from one another. To get a feel for where it sits, imagine the sun as a small lamp on a table. Earth would be a grain of sand about one step away. Mars would be another grain a little farther out. Jupiter, the giant, would be a marble 5 steps from the lamp. The asteroid belt fills the open space between those 2 outer steps. A soft, scattered ring of pebbles, boulders, and the rare small world. In real numbers, most of the belt lies between about 2 and 3.5 times the distance from the sun to Earth. Light from the sun takes around 20 minutes to reach that region. Out there, the sun looks smaller and dimmer than it does from your backyard. The sky is darker. The cold is deep and steady. The rocks themselves come in every size you can imagine. Some are smaller than a grain of rice. Some are the size of pebbles or houses or small mountains. A few are as large as countries. The biggest, a round body called Ceres, is about as wide as the state of Texas, or roughly the distance from London to Warsaw. The next 2, Vesta and Pallas, are each about the size of a small European nation. After those 3, the sizes drop quickly. Most of what remains is rubble. The total mass of the belt is surprisingly small. If you gathered every asteroid together and weighed them, the whole pile would come out to less than 5% of the mass of our moon. That single fact is part of the puzzle this episode keeps circling back to. A ring that wide, with so little stuff in it, is a quiet hint that something strange happened there long ago. The belt is also very old. The rocks within it formed roughly 4.5 billion years ago, around the same time as the sun and the planets. In many ways, the asteroids are leftovers. They are the small pieces that did not get pulled into a bigger world. Some of them have changed very little since then. Others have been heated, broken, and reshaped by collisions over billions of years. For a long time, people had a simple and beautiful story to explain all of this. They thought the asteroid belt was the wreckage of a shattered planet. A world had once spun there, the idea went. Perhaps about the size of Mars, full of rock and metal, and maybe even oceans. Then, in some ancient disaster, it broke apart. The pieces were what we see today, still drifting in the orbit of the lost world. This idea was first proposed in the early 1800s, soon after Ceres was discovered. The astronomer who suggested it, Heinrich Albers, looked at the new little worlds appearing one by one in that same gap and felt that they must belong together. To his eye, they looked like the fragments of a single body. The notion was elegant. It gave the belt a story. It even had a name in popular books for many years. The lost planet was sometimes called Phaeton, after a figure from old myth who fell from the sky. It is a lovely picture to hold in your mind as you settle in. A pale, broken world. A ring of its bones still tracing the path it once walked. For nearly 2 centuries, this was the most common explanation taught in schools and printed in encyclopedias. The trouble is that the numbers do not quite agree with the story. When researchers added up all the mass in the belt today, they found far too little to make a planet, even if you imagined that most of the original body had been flung away over billions of years. The chemistry of the asteroids tells a more complicated tale. Different rocks in the belt seem to have formed in different places, at different temperatures, from different starting materials. They do not look like the broken siblings of one parent world. So the old idea, though beautiful, slowly faded. In its place came new questions. If the belt is not a shattered planet, then what is it? Why does so little matter live in such a wide ring? Why did a world never finish forming there in the first place? Those questions are where the mystery truly begins, and they are where we will wander next. To understand why the asteroid belt looks the way it does, we have to go back to the beginning of the solar system, not to the time of dinosaurs, or to the first humans, or even to the first life on Earth. We have to go back 4.5 billion years, when there was no sun yet, and no planets. Only a vast cloud of gas and dust drifting in the dark. That cloud is what astronomers call the solar nebula. It was made of hydrogen, helium, and tiny grains of ice and rock. For a long time, it simply floated there. Then something nudged it. Perhaps a nearby star exploded. Perhaps a passing wave of pressure squeezed one edge. whatever the cause, the cloud began to fall inward on itself, pulled together by its own gravity. As it fell, it began to spin. Anything that collapses while spinning will flatten into a disk, the way pizza dough flattens when a baker tosses it into the air. The center of this disk grew hot and dense. Pressure built, heat built, and in time, the middle ignited into a young sun. Around that new sun, the rest of the disk kept turning. A wide, glowing plate of dust and gas. This is where the planets would be born. In the warm inner part of the disk, only rock and metal could stay solid. The ice boiled away. So the inner planets, like Mercury and Venus and Earth and Mars, formed from rocky grains. These grains stuck together. They became pebbles. The pebbles became boulders. The boulders became mountains. The mountains became small worlds called planetesimals. Bit by bit, gravity pulled them into the rocky planets we know. But out beyond Mars, something different happened. The grains in that region had every chance to do the same thing. They could have clumped together. They could have built up. They could have, in time, formed another rocky world between Mars and Jupiter. The space was there. The material was there. And yet no planet ever grew. This is one of the quietest mysteries in our solar system. Why did a world fail to form in this one specific place? The leading idea points outward toward Jupiter. Jupiter is the largest planet in our system, and it formed early, while the disk was still rich with gas. Once Jupiter took shape, its gravity reached far across the disk. Anywhere it pulled on, it stirred. And the region just inside its orbit, where the asteroid belt now sits, was stirred the hardest. When Jupiter tugged on the small bodies in that zone, it made them move faster. It changed their paths. Instead of drifting gently and bumping softly, like seeds settling into a slow river, the planetesimals were hurled around. They crashed into each other at high speeds. Instead of sticking, they shattered. Instead of growing, they broke apart. So the picture many researchers favor is this. A planet tried to form there. It started to form there. But Jupiter would not let it finish. Every time the small bodies began to gather, Jupiter scattered them again. Some were flung inward toward the sun. Some were thrown outward into deep space. Some collided so hard they were ground back into rubble. What remains today, all those countless drifting stones, is only a tiny fraction of what once existed. Most of the original material is simply gone. Some studies suggest that the early belt may have held a mass equal to several Earths. Today, if you gathered every asteroid into one ball, it would weigh less than our moon. The rest was lost long ago. There are other ideas too. Some researchers wonder if Jupiter actually drifted inward for a time, sweeping the region almost clean before moving back out and leaving only the leftovers behind. Others think the belt was seeded later with bits of rock that wandered in from elsewhere in the disk. Still, others suspect a quieter story, where the region was always thin, and Jupiter merely kept it from ever recovering. The question of which version is closest to the truth remains open. What we can say, gently and with care, is that the asteroid belt is not the wreckage of a planet that once lived. It is more like the dust of a planet that never got the chance to be born, a construction site that was abandoned before the building rose. The bricks are still scattered there, 4.5 billion years later, drifting in slow circles around the sun. They never came together. They probably never will. And in their stillness, they keep a record of how the planets we know came to be, and how easily, in another place or another time, things might have unfolded very differently. To understand the asteroid belt, it helps to look at what the stones are made of, and to understand that we have to look much further back than the belt itself. We have to look at stars that died long before our sun was born. Every piece of rock drifting between Mars and Jupiter carries atoms that were forged in those ancient furnaces. The early universe held mostly hydrogen and helium, the two lightest elements. Everything heavier came later, cooked inside stars. When a star runs out of fuel, it can collapse and explode, scattering its inner harvest across space. Iron, nickel, silicon, magnesium, carbon, oxygen, all of these were born this way. The asteroid belt is, in a quiet sense, a museum of stellar deaths. When our sun first formed, it pulled together a cloud of gas and dust seeded with these heavier elements. The dust grains were tiny, far smaller than a grain of sand. They held silicates, which are minerals built from silicon and oxygen. They held carbon in dark, soot-like forms. They held flecks of metal, and in the colder outer regions of the young solar system, they held ices made of water, ammonia, and methane. The asteroids gathered up these materials and locked them in place. The inner belt, closer to the sun, holds rockier bodies rich in silicates and metal. The outer belt, further from the warmth, holds darker objects filled with carbon, and in some cases, hidden water. This gradient is one of the quiet clues researchers study when they try to reconstruct the temperature map of the early sun. The minerals inside an asteroid can read like a slow story. Olivine, a green silicate, often points to material that cooled in a certain way. Pyroxene, another silicate, suggests something slightly different. Iron and nickel mixed together hint at bodies that grew large enough to melt inside, letting heavy metals sink toward a core. Some asteroids show all three. Others show only the original dust, barely changed since the solar system began. This is part of why the belt fascinates the people who study it. Most worlds we know have been reshaped by heat, pressure, weather, or living things. The asteroid belt is different. Many of its stones have sat in the cold and dark for over 4 billion years, holding their original chemistry like sealed letters. The link to our own world runs deep. The iron in Earth's core, the iron in your blood, the calcium in your bones. All of these elements came from the same kind of stellar ash that built the asteroids. We are made of the leftovers of stars, and so are they. In that sense, the belt is a distant cousin, formed from the same cosmic pantry. Water is the part of the story that still stirs the most quiet debate. Some asteroids, especially in the outer belt, contain water locked inside their minerals. Researchers wonder if collisions billions of years ago sent water-rich fragments tumbling toward the inner solar system. Some of them may have reached the young Earth, adding to the oceans we know today. Comets may have brought water too. The exact balance between asteroid water and comet water in our seas is still an open question. The chemistry of ocean water is close to that of certain meteorites, which is suggestive picture is not yet complete. Carbon adds another layer. The dark asteroids of the outer belt carry not only carbon itself, but also more complex molecules. Some meteorites that fell to Earth contain amino acids, the small building blocks of proteins. They were not delivered by living things. They formed in space, in the cold and dark, through ordinary chemistry. Whether such deliveries played any role in life's beginnings on Earth is one of the deepest questions in the field. The answer remains unknown. Even the metals matter. The heavier metals found in some asteroids, including small amounts of gold and platinum, were likely forged in even rarer events, such as the collisions of neutron stars. When you look at a small grain of metal in a meteorite, you may be looking at the remnant of a cosmic event that happened in another galaxy long ago. So, when we picture the asteroid belt, it helps to picture not just rocks, but a slow archive, stellar ash, ancient dust, mineral grains older than the sun, water tucked inside crystal structures, faint traces of carbon chemistry that hint at how molecules behave in the dark. Each stone is a small library, and most of those libraries have never been opened. We have read only a few pages, and even those are hard to translate. The rest waits, drifting in the cold between two patient worlds. Among the countless stones that drift in the belt, one stands apart in a quiet, gentle way. Its name is Ceres. It is the largest body in that wide ring between Mars and Jupiter, and it is round. That single fact, that simple roundness, holds a story worth sitting with as you settle into the night. Most asteroids are not round at all. They are lumpy, crooked, shaped like potatoes or peanuts or broken bricks. A small rock does not have enough gravity to pull itself into a sphere. It stays in whatever shape it was left in after the last impact. But Ceres is different. Ceres is large enough and held tightly enough by its own gravity to slowly squeeze itself into a ball. That squeezing is one of the great quiet forces of the cosmos. The process has a soft, slow name. Scientists call it hydrostatic equilibrium. The idea is simple. When a body grows massive enough, its own pull begins to overcome the strength of the rock it is made of. The high places sink, the low places rise. Over long stretches of time, the whole thing settles into the shape that gravity prefers, which is a sphere. Ceres sits right at the edge of that threshold. It is about 940 kilometers across, large enough to round itself, but small enough that it took a great deal of time to do so. Gravity is not the only force at work on this little world. Heat played a role too long ago, when Ceres first formed from the dust and pebbles of the early solar system. It carried within it small amounts of radioactive elements. These elements slowly broke apart, releasing warmth from deep inside. That inner warmth softened the rock and ice, allowing the heavier metals to sink toward the center and the lighter materials to rise. Ceres may have separated into layers, with a rocky core and a softer, ice-rich shell wrapped around it. Whether that layering is sharp and clean or smudged, and partial is still an open question. There is water on Ceres, not flowing rivers, not pooling lakes, but water locked into ice and bound into the chemistry of the rock itself. Some researchers believe that beneath the surface, in pockets and veins, salty liquid may still exist. The evidence comes from strange bright spots inside a crater called a crater. Those spots appear to be made of salts left behind when briny water rose toward the surface, and the water itself drifted away into space. What lies under that crust today remains uncertain. One possibility is a thin, slushy layer. Another is that the interior is mostly frozen now, with only the faintest traces of liquid left. Pressure shapes Ceres too, in its own slow way. At the surface, the pressure is almost nothing, because Ceres has no real atmosphere to speak of. But deep inside, under hundreds of kilometers of rock and ice, the weight of all that material presses inward. That pressure helps lock minerals into certain forms. It keeps ice from behaving the way it would on Earth. Down there, ice can flow slowly, like very cold honey, over the course of millions of years. Radiation also touches Ceres, though more gently than you might expect. The sun is far away from the belt, so its light arrives weaker, paler, less warming. Cosmic rays from beyond the solar system strike the surface and slowly alter the chemistry of the topmost layer. Over billions of years, these tiny strikes break apart molecules, darken fresh material, and leave a faint patina on every exposed face. What Ceres does not have, as far as we can tell, is a strong magnetic field. It does not have the churning metal heart that gives Earth its protective shield, and it does not feel powerful tides because it has no large moon tugging at it from close range. The forces shaping Ceres are quiet ones. Gravity pulling inward, old heat fading, ice flowing in slow currents, light and radiation brushing the surface, grain by grain. The deepest mystery about Ceres is whether it formed where we see it today or somewhere else entirely. Some researchers wonder if Ceres was born in the cold outer solar system and later drifted inward to settle in the belt. Its water content, its chemistry, its strange bright salts, all hint at an origin in colder places. Other researchers think it formed right where it sits now, just a little richer in ice than its neighbors. The question remains open. For tonight, picture Ceres turning slowly in the dark, round and patient, shaped by forces so gentle that no one would ever feel them, yet powerful enough to sculpt a world. After the round, quiet bulk of Ceres, the next great body of the belt is a different kind of world entirely. Vesta is its name, and it is the second most massive object in the asteroid belt. To picture its size, imagine the state of Arizona rolled into a lumpy ball and set spinning in the dark. Vesta is about 330 miles across at its widest. That is roughly the distance from New York City to Pittsburgh, only folded into a single rocky shape, drifting through the cold. Vesta is not round like Ceres. Gravity tried to pull it into a sphere, but the little world was not quite massive enough to win that contest. Instead, it settled into a slightly squashed shape, wider at the middle and flatter at the poles. If you held it in your imagination next to Earth, our planet would be a beach ball and Vesta would be a small marble resting in your palm. Yet that marble holds nearly a third of all the mass in the entire asteroid belt. The surface of Vesta shines more brightly than almost any other asteroid we know. Its face reflects about 4 times more sunlight than our own moon. If if you could float in space beside it, you would see a small, pale, glowing stone, lit by a sun that looks tiny and sharp from that distance. Sunlight at Vesta is only about a seventh as strong as the sunlight you feel on a summer afternoon at home. The world there is dim, cold, and silent, lit by a sun that gives more light than warmth. How cold exactly? The surface of Vesta hovers somewhere around minus 100 degrees Fahrenheit on its warmer side, and far colder in the long shadows. A glass of water set on its surface would freeze in seconds and stay frozen for the rest of time. There is no air, no wind, no sound. Only the faint patter of micrometeorites and the slow turning of the little world beneath the stars. Vesta turns quickly. One full day on Vesta lasts only about 5.33 hours. If you stood on its surface, you would watch the sun rise, cross the dim sky, and set again before your lunch break was over on Earth. That fast spin gives Vesta its slightly flattened shape, the same way a spinning lump of dough widens at its edges. Now think about how far away it sits. Vesta orbits the Sun at an average distance of about 220 million miles. Earth orbits at roughly 93 million miles. So Vesta is more than twice as far from the Sun as we are. A radio signal traveling at the speed of light still takes around 20 minutes to reach Vesta when it lies on the far side of its orbit. A spacecraft moving at the speeds we can build today needs years to make the crossing. Vesta is also extremely old. The best estimates suggest it formed within the first few million years of our solar system's birth, more than 4.5 billion years ago. That is older than every mountain, every ocean, every grain of sand on Earth, older than the moon, older than the oldest rocks anyone has ever held. Vesta has been drifting in roughly its current orbit since long before our planet had a solid crust. And yet, despite its great age, Vesta carries something almost miraculous on its southern half. A vast crater stretches across that region, nearly as wide as the asteroid itself. The basin is called Resilvia, and it is one of the largest impact craters in the entire solar system, scaled to the body that holds it. Some long ago collision struck Vesta so hard that it nearly broke the little world apart. Pieces flew off into space, and many of them eventually found their way to Earth as meteorites. There may be small fragments of Vesta sitting quietly in museum drawers right now. How that collision happened, when exactly it happened, and why Vesta survived it instead of shattering, these remain open questions. One idea is that the impact occurred roughly 1 billion years ago. Another suggests it happened in 2 separate events, layered one on top of the other. The crater walls preserve clues, but the full story has not been settled. So picture this bright, fast-spinning, cold, ancient stone the size of a small country, scarred by a wound nearly as wide as itself, glowing faintly in the dark between Mars and Jupiter. It has been turning there quietly since before life on Earth even began. And we are still trying to understand what happened to it and what it has to tell us about the long, slow making of worlds. Imagine drifting in slow silence above a strange gray world far from the sun, where the light is dim and cold and falls at an odd angle. This is Pallas, the 3rd largest body in the asteroid belt, and one of the most puzzling places in the inner solar system. From a distance, it looks like a slightly squashed ball of dark stone, almost 300 miles across. Its color is something close to charcoal, with patches of a paler gray, like ash mixed into soot. There is no atmosphere to soften the view, no clouds, no wind, just the bare rock and the steady black of space beyond. If you could float closer, you would see that Pallas is not smooth like Ceres. Its shape is uneven, lumpy in places, as if it had been gently squeezed by some long-forgotten force. Craters cover its surface in overlapping rings, large ones holding smaller ones inside them. Some scientists have nicknamed it the golf ball asteroid, because the entire surface seems pocked and dimpled, scarred again and again by ancient impacts. Each crater is a memory of a collision that happened millions or billions of years ago, when the belt was a far more crowded and violent place. The strangest thing about Pallas is not its surface, though. It is the way it moves. Most of the larger asteroids orbit the sun on roughly the same flat plane, like marbles rolling on a table. Pallas does not. Its orbit is tilted by about 34 degrees, a steep angle that carries it up and out of the main crowd of stones, then back down through them again. It is a wanderer in the truest sense, a body that does not quite belong to the gentle disk where its neighbors drift. Why Pallas moves this way is an open question. One idea is that some early collision tipped it long ago, knocking it onto a tilted path and leaving it there. Another possibility is that the gentle, repeating tug of Jupiter over countless millions of years slowly lifted Pallas out of the plane. A third thought is that Pallas was never quite in the plane to begin with, that it formed in a slightly different region and was nudged into its current orbit during the chaotic early days of the solar system. None of these ideas is fully proven. The tilt remains one of the small mysteries that scientists return to again and again. Pallas is not alone in its tilted wandering. There are many smaller asteroids that share this strange habit, orbits that lean sharply away from the flat belt. Astronomers sometimes call these the Pallas family, a group of stones thought to share a common origin. They may be fragments knocked loose from Pallas itself during some ancient impact, or they may be cousins from a similar formation event. Their colors and compositions match in ways that hint at a shared past, but the full story of how the family came together is still being pieced together, one faint observation at a time. To stand on Pallas, if such a thing were possible, would be a quiet experience. Gravity there is weak, only a fraction of what we feel on Earth. A single careful step might lift you slowly off the ground and carry you in a long, drifting arc. The horizon would curve sharply away. Because the world is small, the sun would look distant and pale, less than a fifth as bright as it appears from Earth, and the sky around it would be filled with stars even in the middle of the day. Other asteroids would be too far to see clearly, just faint points of light moving slowly against the dark. The surface itself would feel ancient under your boots. Loose dust, called regolith, covers much of it, ground down by countless tiny impacts over the ages. Larger rocks would sit half buried, some sharp-edged, some softened by long exposure. The dark color of the surface suggests that Pallas is rich in carbon and possibly in water-bearing minerals, though much of this is inferred from telescopes rather than confirmed by visits. No spacecraft has ever landed on Pallas. Everything we know about its surface comes from light, from spectra, and from a handful of careful images taken from very far away. That distance is part of what makes Pallas so quietly compelling. It is a world we have seen but never touched, a tilted traveler moving on its own private path through the belt. It carries its scars and its dust and its small family of cousins through the cold, and it keeps its secrets close. For tonight, it is enough to picture it turning slowly in the dim sunlight, a gray stone wandering above the plain, waiting. If you could drift slowly through the asteroid belt and look closely at the stones around you, a quiet pattern would begin to emerge. The rocks would not all look the same. Some would be dark, almost as black as soot. Others would be pale gray, the color of old bone, and a few would shine with a soft metallic gleam, like dull mirrors hanging in the dark. Astronomers sort the asteroids into 3 broad families based on what they seem to be made of, and each family hints at a different chapter of the early solar system. The first and largest family is known as the C-type asteroids. The C stands for carbon. These dark stones make up roughly 3/4 of all known asteroids in the belt. They reflect very little light. If you held one in your hand, it would feel almost like a lump of charcoal, warmed by a faint inner glow. Most of them sit in the outer parts of the belt, farther from the sun, where the early solar system was cooler. Researchers think these dark bodies hold some of the oldest unchanged material from the cloud that formed the planets. Water may be locked inside them, bound up in clays and minerals. But the deeper structure of these dark stones is still mostly a mystery. Telescopes can only read the surface. The second family is the S-types. The S stands for stony, or sometimes silicate. These are the pale ones, made of rock rich in silicon and traces of metal. They tend to live in the inner part of the belt, closer to Mars. Many of the meteorites that fall to Earth seem to come from this group. Under a microscope, slices of them show tiny round beads of once melted rock, frozen in place for billions of years. Why these stony bodies cluster nearer the sun, while the dark carbon ones drift farther out, is part of the larger riddle of how the belt sorted itself. One idea is that the early sun was hotter than expected and baked the lighter elements out of the inner asteroids. Another idea is that the inner and outer belts formed in different places and only later mingled. The third family is the rarest and the strangest. These are the M types, and the M stands for metallic. They shine in radar like polished coins lost in the dark. Some of them seem to be almost pure iron and nickel, the kind of metal you might find at the heart of a planet. And that is exactly what they may be. The leading theory is that these metal worlds are the broken cores of small bodies that grew large enough to melt inside, sorted their heavy metal toward the center, and then shattered when something hit them long ago. The lighter outer layers were stripped away, leaving only the dense core exposed to space. If that theory is correct, the M types are like windows into the buried hearts of planets that never finished forming. But not every astronomer agrees. Some recent measurements suggest a few of these metal-looking asteroids may have more rock in them than expected. The picture is still being redrawn. Beneath the surface of any of these bodies, things grow stranger still. A C-type asteroid may hold pockets of frozen water mixed with grains of soot, untouched since the sun was young. An S-type may hide a deep layer of crushed rubble ground fine by countless slow collisions beneath a thin crust of older stone. An M-type may be a single, almost solid lump of metal, ringing faintly when struck, like a great bell drifting silently through the dark. No one has ever drilled into one. No probe has yet cut deep into the inside of an asteroid to see what is truly there. Almost everything we believe about their hidden interiors comes from light, radar, gravity, and a few precious samples returned to Earth in tiny sealed capsules. And there is a quieter question that sits underneath the three families. Are these really three separate groups? Or are they shades of a single story blurred together by time? Some asteroids do not fit neatly into any class. A few seem to be hybrids, with dark patches on bright surfaces or metallic streaks running through stone. The boundaries between the families may be softer than the simple letters suggest. So, as you drift in your imagination through this slow cloud of rocks, picture them sorted into dark, pale, and shining, but only loosely. Each one carries a piece of the early solar system inside it, and each one is still, in many ways, a closed book waiting quietly for someone to open it. Three families of stone drift through the belt, and each one tells a different story about how it formed. The carbon-rich ones, the stony ones, and the metal ones. They are not scattered at random. They follow a pattern, a kind of gentle gradient that stretches outward from the sun. And within that pattern lies one of the belt's quiet rhythms, a cycle written into the very chemistry of these ancient rocks. Closer to the inner edge of the belt, the stony asteroids tend to gather. These are the bright ones, made of silicate minerals, much like the rocks beneath our feet. They formed in a warmer part of the young solar system, where the heat of the early sun drove away the lighter, more fragile materials. What remained was stone, baked and hardened, holding the memory of that warmer place. Move outward, and the character of the belt slowly shifts. The carbon-rich asteroids become more common. They are darker, often blacker than coal, soaking up nearly all the light that touches them. They formed farther from the sun, where temperatures were cooler, and where carbon and water and other delicate compounds could survive without being burned away. These dark wanderers may be the most pristine objects in the entire solar system. Some researchers think they have changed very little in over 4 billion years. Then there are the metal ones. These are the rarest of the three, but the most striking. They appear to be made largely of iron and nickel, the kind of materials you would expect to find at the heart of a small planet. One leading idea suggests that they are exactly that. The exposed cores of bodies that once grew large enough to melt inside, only to be shattered later by collisions, leaving behind only their dense metallic hearts. If that theory holds, the metal asteroids are like windows into worlds that almost were. Tiny planets that never never finished growing. The arrangement of these three families seems to record the temperature gradient of the early solar system, a frozen snapshot of how the young sun warmed its surroundings, with each zone of warmth giving rise to a different kind of rock. The belt, in this view, is a kind of geological diary, each page written at a different distance, at a different temperature, in a different chemical mood. But the cycle does not end there. Over billions of years, collisions have stirred the belt, breaking large asteroids into smaller ones and scattering their fragments across orbits they were never born into. A stony asteroid might be flung outward. A carbon-rich one might drift inward. The original neatness has been smudged by time, and so the question becomes harder to answer with certainty. Are the families still where they formed, or have they all wandered? How much of the pattern we see today reflects the early solar system, and how much reflects the long, slow shuffling of 4.5 billion years of gentle chaos? There is another rhythm hidden in this chemistry. The carbon-rich asteroids hold water, locked inside their minerals in tiny amounts. When these objects collide, or when they pass close to the sun, that water can be released. Some researchers wonder whether the inner solar system, including the early Earth, received much of its water from objects like these, delivered slowly in small parcels over hundreds of millions of years. The cycle of carbon and water and stone may stretch from the belt all the way to the oceans of our own world. Whether that is truly how Earth got its water remains an open question. There are other ideas, too, involving comets from much farther out, and the possibility that water was simply present from the beginning. The evidence is still being gathered. The metal asteroids carry a different kind of memory. If they really are the cores of broken worlds, then their existence implies a violent past, an era when collisions were common and large bodies regularly tore each other apart. The belt today is far quieter than it once was. The pulse of impacts has slowed, but the metal cores still drift, cold and dense, holding within them the chemistry of a long-vanished beginning. So the belt breathes in slow rhythms, warm and cool, light and dark, stone and carbon and metal, each family pointing back to a different chapter of formation, each chapter still only partly read. The asteroids do not give up their secrets quickly. They keep their stories deep inside, in the patterns of their minerals, in the ratios of their elements, in the quiet arrangement of their orbits. We have begun to listen. We are still learning the language. When most of us picture the asteroid belt, we picture a crowded place. We see a thick ring of tumbling stones, knocking into each other, sparks flashing in the dark. It is one of the most common images in stories about space, and it is one of the most misleading. The real belt is mostly empty, so empty, in fact, that if you stood on one asteroid and looked around, you would almost certainly see nothing else at all. No other rocks, no silver glimmer of a neighbor, only the distant sun, smaller and dimmer than it looks from Earth, and the deep starfield beyond. This emptiness is hard to imagine because the numbers seem to argue against it. There may be more than 1 million asteroids in the belt, larger than 1 kilometer across. Add in the smaller ones, and the count climbs into the billions. Yet the belt is enormous. It stretches across a band of space hundreds of millions of kilometers wide, and just as tall, and wraps all the way around the sun. Spread 1 million stones through that volume, and the average distance between them becomes vast, hundreds of thousands of kilometers, sometimes more. The belt is a ring of solitude, not a swarm. This quiet emptiness shapes everything about how the belt behaves. Collisions do happen, but they are rare. A given asteroid might wait hundreds of millions of years between serious impacts. In the meantime, it simply drifts. It turns slowly in the sunlight. It traces its long, patient orbit around the sun, never hurrying, never crowded. The neighbors of the belt are equally distant and equally important. On the inner edge lies the orbit of Mars, a small red world with thin air and frozen poles. On the outer edge looms Jupiter, the giant. These two worlds act like soft walls. Mars tugs gently on the inner asteroids. Jupiter pulls far more strongly on the outer ones. Between them, the belt stretches like a quiet field, shaped by forces it cannot resist. The relationship with Jupiter is the more dramatic of the two. Jupiter's gravity reaches deep into the belt. It bends extends orbits, stretches them, and in some places empties them out completely. Some researchers think Jupiter has been doing this since the very beginning. Others wonder if Jupiter itself once wandered closer to the Sun, swept through the inner belt, and then drifted back out. That idea, sometimes called the Grand Attack, remains an open question. The evidence is suggestive, but not certain. If it is true, then much of what we now see in the belt is the leftover trace of that ancient migration. Above and below the belt, there is even more emptiness. The belt is not perfectly flat. Some asteroids ride along the same plane as the planets. Others tilt above or below it, sometimes by 20 degrees or more. Pallas, one of the largest bodies, leans on a sharp angle. These tilted wanderers spend much of their lives far from the main crowd, alone in regions where the belt thins to almost nothing. Beyond the outer edge, the belt fades into another quiet zone. Past Jupiter, the small icy worlds called the Hildas trace, looping paths in step with the giant planet. Farther out still are the Trojan asteroids, which share Jupiter's orbit and ride in two great clouds ahead of it and behind it. Whether these distant cousins formed with the belt or were captured from somewhere else is still debated. Some researchers think the Trojans came from the outer solar system, swept inward during a long ago shuffling of the planets. Others think they formed where they sit. The samples we have are too few to settle the matter. Closer to home, the belt also reaches inward. A few stray asteroids slip free of the main band and wander into the inner solar system. Some cross the orbit of Mars. A small number cross the orbit of Earth. They are the near-Earth asteroids, and they are the most studied because they are the closest. But they remain a tiny fraction of the whole. The belt itself, the great quiet field between Mars and Jupiter, almost never sends its residents very far. So the asteroid belt is not a crowded place. It is a hushed one, a wide, slow, mostly empty ring, bordered by a small red world on one side and an enormous striped giant on the other, with each stone keeping a polite, almost lonely distance from its neighbors. The mystery of how it came to be this way, and not some denser thing, is part of what makes it worth wondering about as you drift toward sleep. asteroid belt did not come from telescopes or spacecraft. It came from stones that fell to Earth. Meteorites are the quiet messengers of the belt, small pieces of rock and metal that crossed the long dark and landed in deserts, ice fields, and farmyards. Each one is a letter from a world that never finished forming. And the oldest of these letters carry record-breaking news. The most surprising thing about meteorites is their age. The oldest solid grains ever measured inside them are about 4.5 billion years old. These tiny specks formed before the planets did. They are older than Earth itself. They are older than the sun's steady burning shape. When you hold a primitive meteorite, you are holding a piece of matter that predates every rock beneath your feet. Nothing on our planet's surface comes close to that age. The belt has been keeping these grains safe for us in deep, cold storage since before there was a here. Some meteorites are also among the coldest objects ever to touch the ground. Before they fell, they spent billions of years drifting in the outer belt, where sunlight is faint and temperatures hover far below anything you have ever felt. The frost locked into their pores has not melted in eons. When researchers cut these stones open in clean labs, they sometimes find tiny pockets of water still trapped inside. Water that may be older than the oceans. One open question is how much of Earth's water arrived this way, riding inside cold, dark rocks during the chaotic early years. Then there are the iron meteorites, which carry a different kind of extreme. These are the densest natural objects most people will ever encounter. A small chunk no larger than a fist can weigh as much as a brick. They are mostly iron and nickel, woven together in long crystal patterns that take millions of years of slow cooling to form. Those patterns only grow inside the molten cores of small worlds, which means each iron meteorite is a fragment of a shattered protoplanet. A tiny world that once had a heart of metal before something broke it open. We do not know how many such worlds once drifted in the belt. Estimates range widely, and the question remains open. The fastest meteorites strike the atmosphere at speeds of more than 70 kilometers per second. At those speeds, the air itself becomes a wall. The stone heats, glows, and sheds its outer layers in seconds. Most arrive much slower, but even a gentle entry is far faster than any aircraft. What lands on the ground is often only a small remainder of what entered the sky. The rest is light and sound, scattered across the upper air. The rarest meteorites are the ones called carbonaceous chondrites. They are dark, soft, and crumbly, and they contain something extraordinary, complex carbon compounds, including amino acids, the small molecules that life on Earth uses to build proteins. These are not life. They are the ingredients for the chemistry of life. Some researchers wonder whether such meteorites seeded the young Earth with the parts it needed to begin. Others think Earth made its own ingredients in shallow ponds or near hot vents. The question is genuinely unresolved, and the carbonaceous meteorites sit at the center of the debate. A few meteorites are stranger still. Some appear to come from Vesta, the bright asteroid we visited in an earlier section. Their chemistry matches Vesta's surface so closely that researchers feel confident in the link, though confident is not the same as certain. A handful of others may come from Ceres or from objects that no longer exist. Each rare type adds another voice to the belt's quiet chorus. The smallest meteorites are dust. Tiny grains, finer than flour, drift down through the atmosphere every day. Many tons of this material settle on Earth each year, mostly unnoticed. Some of it lands on rooftops. Some of it lands on you. The belt is, in a quiet way, still arriving. What makes these letters so precious is that we cannot yet read them fully. The chemistry inside a single meteorite can take decades to analyze. New techniques reveal new clues. Older stones, kept in museum drawers for a century, are being studied again with fresh eyes. One possibility is that the answer to how the belt formed is already sitting in a lab somewhere, waiting for the right question. Another is that the truly important stones have not yet fallen. For now, the belt keeps writing, and Earth keeps catching the letters, one cold, quiet stone at a time. There is a quiet detail about the asteroid belt that took a long time for anyone to notice. Many of those old, broken stones carry water inside them. Not lakes, not oceans, oceans. Just water locked into the structure of the rock itself, held in place for more than 4 billion years. To understand this, picture a small dark asteroid drifting slowly between Mars and Jupiter. From the outside, it looks like a lump of coal, rough and dim, reflecting almost no sunlight. But deep inside the mineral grains, water molecules sit bonded to atoms of other elements. The rock is not wet. It is hydrated. The water is part of the stone, the way moisture can be part of clay. Scientists learned about this in 2 ways. They studied the light bouncing off dark asteroids and noticed a faint dip at certain wavelengths, a small fingerprint left by water bonded into minerals. And they studied meteorites that had fallen to Earth, especially the carbon-rich ones, and found tiny veins of clay and salt running through them. These veins are signs that liquid water once flowed inside the parent asteroid long ago, before the rock cooled forever. That last part is the wonder. For water to leave veins in stone, it had to be liquid at some point. And for water to be liquid, something had to warm the inside of the asteroid. The leading idea is that radioactive elements baked into the rock when the solar system was young slowly released heat as they decayed. That gentle inner warmth was enough to melt buried ice for a brief window of time, perhaps only a few million years. Then the heat faded, the water froze or escaped, and the asteroid grew cold and still. The question of how much water the belt holds in total remains open. Some researchers estimate the dark asteroids could contain a small ocean's worth, scattered across countless bodies. Others suspect the number is much lower, since we have only sampled a tiny fraction of the population. The truth is hidden in stones we have not yet visited. Beneath the microscope, the details grow even smaller and more beautiful. Slices of carbon-rich meteorites show tiny round beads called chondrules, frozen droplets of melted rock, no wider than a grain of sand. Around them sit even smaller white specks, calcium aluminum inclusions, which are the oldest solid objects ever found in the solar system. They formed before the planets, before the sun finished settling into its current shape. Each speck is a fossil from a vanished moment. Threaded between these ancient beads, scientists find the soft, pale lines of clay minerals. Those lines are where the water once moved. If you trace them under a microscope, you are following the path of a stream that flowed inside a stone the size of a small mountain more than 4 billion years ago in the dark cold of space. Some meteorites carry even quieter surprises. Tiny organic molecules, including amino acids, sit tucked into the carbon-rich layers. Amino acids are the small building parts that living cells use to make proteins. Finding them inside an asteroid does not mean the asteroid was alive. It means the chemistry that life uses was already cooking inside these rocks before Earth had oceans. Whether that chemistry helped life begin on our planet or simply ran in parallel and never went anywhere remains an open question. There are also the colors, faint and easy to miss. Under careful imaging, the dust on a hydrated asteroid can show subtle blue and gray tones, slightly different from the dry stones nearby. Spacecraft that have visited such bodies up close report soft, powdery surfaces, almost sponge-like, full of small pits and dark grains. The texture suggests rock that has been gently soaked and dried and shaken for ages, never fully crushed, never fully hardened. What makes all this quietly moving is the scale. We are talking about water held inside crumbs of stone, drifting in a region so empty that the asteroids almost never see each other. Each hydrated body is its own tiny museum, carrying a record of warmth and chemistry from a time before our world existed. And we have only opened a few of those museums so far. Whether the belt's water once helped fill Earth's oceans is still debated. Some isotope measurements match. Others do not match perfectly. The story is incomplete and may stay incomplete for a long time. For now, it is enough to know that out there, in the dim space between Mars and Jupiter, ancient stones hold ancient water in their bones. They turn slowly. They keep their secrets, and the smallest grains inside them remember a warmth the rest of the belt forgot. In the late 1700s, astronomers had begun to suspect that something was missing between Mars and Jupiter. The gap between those two worlds seemed too wide, too empty, too quiet. A pattern in the spacing of the planets, noticed by a few careful observers, hinted that a body ought to live there. So a small group of European astronomers organized themselves into a kind of nightly watch, sweeping the sky patch by patch, looking for whatever might be hiding in that long stretch of dark. They never found a planet. What they found instead, beginning on the very first night of the 1800s, was Ceres, then Pallas, then Juno, then Vesta, 4 small points of light, each drifting through the same broad lane between Mars and Jupiter. For a while, astronomers called them planets too. But as the count kept rising through the next century, it became clear that this was something else entirely. A scattering, a swarm, a region rather than a world. By the 1800s, telescopes had improved, and the catalog of small bodies kept growing. With every new discovery, astronomers began to write down not just where each asteroid was on a given night, but the full shape of its orbit, how far it traveled from the sun, how long it took to complete one loop, how tilted its path was compared to the flat plane of the planets. Slowly, a great list of orbits took form, scratched into ledgers by candlelight and lamplight. It was in this growing list that a quiet American astronomer named Daniel Kirkwood noticed something strange. He was studying the orbital periods of the known asteroids, the time each one took to circle the sun. When he sorted them by that period and looked at the pattern, he saw gaps. Not gaps in space exactly, but gaps in the count. Certain orbital periods had almost no asteroids in them at all, while the periods just on either side were crowded. Kirkwood looked closer, and he saw that these empty zones matched simple fractions of Jupiter's own year, an asteroid that orbited the sun in exactly half the time Jupiter took, an asteroid that orbited in exactly 1/3 of Jupiter's year. Those special orbits, the ones tuned to Jupiter's rhythm, were nearly empty. The asteroids seemed to avoid them. He proposed an explanation that still holds up today. When a small body orbits in a neat fraction of Jupiter's period, it meets Jupiter again and again at the same point in its loop. Each meeting is a small tug. The tugs add up. Over millions of years, those small repeated pulls slowly stretch the orbit, tilt it, eventually fling the asteroid into a new path far from the gap. The empty lanes are not empty because nothing ever entered them. They are empty because nothing can stay. These quiet stripes in the belt came to be called the Kirkwood gaps. They were one of the first clear signs that the asteroid belt was not a random scatter, but a shaped thing, sculpted by an unseen hand of gravity, reaching across more than 300 million miles. Yet, even with this beautiful idea in place, mysteries remained. Some of the gaps clear out quickly in computer models in only a few 100,000 years. Others should hold their asteroids for much longer, and yet they too are empty. The exact path by which a stone is removed, the precise mix of nudges that lifts it out of the belt forever, is still being worked out. Some bodies seem to spiral inward toward the sun. Others get tossed outward into the cold reaches beyond Jupiter. A few may rain down on the inner planets long after they leave the gap. There are also nearby places where asteroids do gather, locked into Jupiter's rhythm rather than chased away by it. These crowded spots and the empty gaps live side by side, governed by the same math, yet leading to opposite results. Why some resonances trap and others scatter is a question astronomers still circle, refining their models year after year. When you picture the belt now, picture it the way Kirkwood first saw it in his careful columns of numbers. Not a smooth ring of rubble, but a faintly grooved disk, with bands of crowding and bands of silence. Each silent band is a long, slow argument between a tiny stone and the largest planet, an argument the stone always loses, given enough time. The instruments have grown since then. Photographic plates, then digital sensors, then space telescopes. The list of known asteroids has climbed past 1 million, but the gaps remain, dark and patient, still teaching us how gravity writes its quiet rules into the bones of the solar system. When most people picture the asteroid belt, they imagine that one ring of stone between Mars and Jupiter, and they stop there. The truth is stranger and far more crowded. The space around Jupiter holds whole other swarms of asteroids, hidden in plain sight, sharing the giant planet's path in ways that took astronomers a long time to even notice. These hidden crowds change the whole story of the belt because they suggest the rocky leftovers of the solar system did not all settle in one neat lane. The largest of these hidden swarms are called the Trojans. They do not orbit Jupiter the way a moon would. Instead, they ride along Jupiter's own orbit around the sun, gathered into two great clouds. One cloud rides ahead of Jupiter, 60 degrees in front. The other cloud trails behind, 60 degrees back. These two spots are special places in space where the pull of the sun and the pull of Jupiter meet in a quiet balance. Anything that drifts into one of these spots tends to stay there, gently held in place by gravity from two directions at once. The strange part is the sheer number of them. Current estimates suggest there may be roughly as many Trojan asteroids as there are objects in the main belt itself. A second belt hiding alongside Jupiter, almost the same size as the famous one, and most people have never heard of it. The Trojans are dim and dark, harder to see, painted in deep reddish browns. For a long time, no one knew they were there at all. Then there are the Hildas. The Hildas live in a strange three-cornered dance. They orbit the sun in such a way that for every 2 trips Jupiter makes around the sun, the Hildas make 3. This locked rhythm pulls them into a slow, shifting triangle pattern. If you could speed up time and watch them from far above, the whole Hilda group would trace out the shape of a rounded triangle, with one corner near Jupiter's leading Trojan cloud, one corner near the trailing cloud, and one corner on the far side of the sun. The triangle slowly rotates as the planets move. It is one of the quieter geometries in the solar system, and it only exists because of that gentle 3-2 pull from Jupiter. Further out beyond Jupiter sit the centaurs. These are icy, rocky bodies that drift among the outer planets, crossing the orbits of Saturn, Uranus, and Neptune. They do not really fit any category. Some researchers think the centaurs began their lives much farther out, in the cold belt beyond Neptune, and slowly fell inward over millions of years. Others wonder if some centaurs may be ancient bodies pushed outward from closer in. Their true origin is still an open question. What makes all of this strange is what it suggests about the main belt itself. The classical picture said the asteroid belt was simply the leftover rubble between Mars and Jupiter. But the Trojans, the Hildas, and the Centaurs suggest the early solar system scattered its leftovers across many lanes, not just one. Small bodies got caught in gravitational pockets all over the place, like dust settling into the corners of a quiet room. Even stranger, the Trojans may not have been born where they now sit. One leading idea is that they were captured. According to this theory, Jupiter migrated across the early solar system, shifting its orbit inward and then outward again. As it moved, it swept up small bodies from other regions and locked them into those two stable points ahead and behind. If that idea is right, then the Trojans are not Jupiter's siblings at all. They are travelers from somewhere else, frozen in place by a chance arrangement of gravity. Other researchers favor different explanations, and the question of where the Trojans truly came from is not yet settled. The Hildas raise their own quiet puzzle. Their composition looks different from the main belt's inner asteroids. They tend to be darker, more carbon-rich, more like the bodies of the outer solar system. Some scientists wonder if they too were nudged inward from farther out, then locked into their 3-2 rhythm and left there. The evidence is still incomplete, so the simple picture of one belt, one ring, one neat band of rubble dissolves the more closely we look. The solar system seems to have many small swarms, each held in place by its own balance of forces, each hinting at a more chaotic past than the calm orbits suggest today, where each swarm truly came from, and how they sorted themselves into these quiet pockets remains a mystery we are still slowly piecing together. One dark, drifting stone at a time. For most of the last century, the picture of our solar system was a peaceful one. The planets formed roughly where we see them now, each settling into its own quiet lane, like marbles dropped into grooves cut long ago. The asteroid belt was simply what was left between Mars and Jupiter, a thin ring of stones that had stayed put for billions of years. It was a tidy story. It may also be wrong. Over the past 2 decades, a different idea has gained ground. Some researchers now suspect that the giant planets did not stay where they were born. Instead, they may have wandered. Jupiter, Saturn, Uranus, and Neptune might have drifted inward and outward through the young solar system, swept along by the gas and dust that once filled the space between them. If that is true, then the asteroid belt we see today is not a simple leftover. It is the wreckage of a much larger story, a place stirred and reshaped by giants passing nearby. One version of this idea is sometimes called the Grand Migration. In this picture, Jupiter formed farther out, then slowly fell inward, perhaps as close to the Sun as Mars is today. Saturn, growing behind it, eventually caught up. The two giants locked into a slow gravitational dance, and together they reversed course, drifting back outward to roughly where they sit now. As Jupiter swept in and out, it would have plowed through the early asteroid belt twice. The first pass scattered the inner rocks. The second pass mixed in icy bodies from farther out. By the end, the belt held only a small fraction of its original mass, with rocky and icy worlds tumbled together in the same ring. There is another version, sometimes called the late instability. In this picture, the giants stayed roughly in place for hundreds of millions of years. Then something tipped the balance. Their orbits shifted, and a wave of disturbance rippled outward and inward. The belt was stirred again, and many of its members were flung away. Some struck the inner planets, leaving the heavy cratering we still see on the moon. Some were tossed into long, lonely orbits at the edge of the system. Some simply fell into the sun and were lost. Both ideas share a quiet thread. They suggest that the belt is not a still pond, but a place that has been rippled by forces far larger than itself. Jupiter, in particular, seems to act like a slow hand stirring a bowl. Its gravity reaches across hundreds of millions of miles. It tugs on every rock in the belt, year after year, century after century. Over long stretches of time, those tugs add up. They open the Kirkwood gaps. They nudge stones onto crossing paths. They send some inward toward the sun, and others outward toward the cold. The same pattern seems to play out at larger scales. Around other stars, astronomers have spotted dusty rings that look much like our own belt. Some of those rings sit close to the star. Some sit far out in the cold beyond. Many show gaps and clumps that hint at unseen planets stirring them, just as Jupiter stirs ours. If the migration ideas are right, then what we see in our belt is not unique. It may be a common signature of giant planets growing, shifting, and settling. Each system would carry its own scars, its own scattered stones, its own quiet record of how its worlds found their places. There are pieces of evidence that fit the migration idea well. The mixed nature of the belt, with dry, stony bodies sitting beside damp, carbon-rich ones, is hard to explain if everything formed in place. The small total mass of the belt, far less than a single proper planet, fits a history of scattering. The heavy cratering on the moon and inner planets fits a late stirring. Yet none of this is proof. The timing is uncertain. The exact paths of the giants are uncertain. Computer models can produce many possible histories, and each one leaves slightly different fingerprints. So the belt becomes a kind of witness. Every rock in it carries a memory of where it formed and what pushed it into its current orbit. By studying those rocks, by mapping their families and their chemistry, researchers hope to read that memory back into a story. The story is still being written. The migration may have been grand or gentle or something else entirely. What seems clear is that the belt did not form alone. It was shaped by the slow, patient pull of distant worlds, and it still holds the echoes of their long walk through the early solar system. Nothing in the belt stays still. The stones drift on their long, slow paths around the sun, and over millions of years, some of them slip free. They wander inward toward the warm inner worlds. They wander outward into the cold. The belt we see tonight is not the belt that existed 1 billion years ago, and it is not the belt that will exist 1 billion years from now. It is a slow river of rock, always losing pieces, always being reshaped by forces too gentle to notice on any human timescale. The main way a stone wanders inward begins with a small nudge. 2 asteroids drift close. They do not always collide. Sometimes one simply tugs the other with its tiny gravity. shifting its path by the faintest amount. That shift may carry it into one of the Kirkwood gaps, where Jupiter's pull repeats again and again in perfect rhythm. Once inside that rhythm, the stone's orbit begins to stretch. Slowly, across thousands of years, the path grows longer and more oval. The stone now crosses into the inner solar system, drifting closer and closer to Mars, and sometimes to Earth. There is another force at work, and it is one of the gentlest forces in all of space. Sunlight itself can move an asteroid. When a small rock spins under the sun, one side warms during the day and slowly releases that warmth as it turns into night. The heat leaves as a faint glow of infrared light, and that glow carries a whisper of push. Over millions of years, this whisper adds up. A stone the size of a city block can drift across enormous distances, simply because it is warmed unevenly by sunlight. Researchers call this effect by a long name, but the idea is simple. Light is a feather. Time is patient. Together, they move mountains. Some of the wanderers become what we call near-Earth asteroids. These are stones whose orbits now cross or nearly cross our own. Many of them were once quiet residents of the belt. They left their birthplaces long ago, drifted inward through resonance and sunlight, and now loop through the warmer parts of the solar system on borrowed time. Their visits are not permanent. Eventually, most will fall into the sun or crash into a planet or be flung back out by a close pass with Jupiter. The inner solar system is a temporary home for these travelers. The question of how often this has happened and how often it still happens remains open. One idea holds that the early solar system saw a sudden wave of inward wanderers, a period when the belt lost a great many of its members all at once. Some researchers point to the cratered faces of the Moon and Mercury as evidence of this ancient storm. Other researchers wonder whether the wandering has always been steady, a quiet trickle rather than a flood. The cratering record is hard to read with certainty. The stones do not leave dates on the wounds they make. There is also the question of where the wanderers come from within the belt itself. Some appear to be fragments of the same parent body, sharing similar colors and orbits. These are called family can supply visitors to the inner solar system for hundreds of millions of years after its parent breaks apart. One possibility is that much of the rocky debris reaching Earth today traces back to just a handful of ancient collisions, long vanished worlds whose pieces are still slowly arriving. Another possibility is that the sources are far more scattered, and that no single ancestor dominates the traffic. The evidence remains incomplete. Even now, as you listen, stones are shifting. Somewhere in the belt, two small bodies are drifting past one another, exchanging a faint gravitational greeting. Somewhere a sunlit rock is releasing a sigh of infrared warmth into the dark, nudging itself by a fraction of an inch. None of this is visible from Earth. None of it could be felt by a hand resting on the surface of one of these stones. The changes are too slow, too quiet, too patient. Yet they are real, and they have been happening for 4.5 billion years, and they will keep happening long after every human story has ended. The belt we picture as a frozen ring is really a slow procession. It loses members and gains them. It sends pieces inward to warm against the sun and outward into the long cold. The faces of the inner planets carry the marks of these wanderers. The mystery of how many came, and when, and from where, drifts along with them, unresolved, turning gently in the dark. Light is the oldest messenger in the universe. It carries news across distances so vast that the news itself is ancient by the time it arrives. When sunlight finally reaches the asteroid belt, it has already traveled for about 25 minutes, give or take, depending on where the rocks are drifting in their slow orbits. That light touches each stone and bounces back into the dark, carrying with it the faint signature of what the stone is made of. And in those signatures, scientists believe, is a record of the early solar system itself. The belt does not glow. It does not shimmer like a nebula or burn like a sun. It only reflects. Each asteroid is a small, dim mirror, returning a little of the light that strikes it. But that little is enough. By spreading the reflected light into its colors, the way a prism spreads sunlight into a rainbow, astronomers can read what minerals lie on the surface. Dark carbon-rich rocks soak up most of the light, and send back only a dim red-brown whisper. Stony asteroids return a paler, warmer tone. Metal-rich bodies shine with a colder, harder gleam, like polished iron left out in the cold. This is why many call the belt a time capsule. The light it reflects is, in a sense, light from the beginning. The rocks themselves formed in the first few million years of the solar system, and most have changed very little since. They never grew large enough to melt fully. They never built atmospheres that would weather their surfaces. They simply waited, drifting in the quiet, holding their original chemistry in place. When sunlight strikes them now, it picks up the fingerprint of that ancient moment and carries it back across the dark to our telescopes. What that fingerprint actually means is still being worked out. One idea is that the colors we see truly reflect where each asteroid first formed. Darker, carbon-rich bodies, by this thinking, came together farther from the young sun, where ices and organic molecules could survive. Brighter, stonier ones formed closer in, where the heat drove off the more delicate ingredients. If this picture is right, then the belt is a kind of sorted library, with chapters from different regions filed in their original order. Another possibility complicates that neat story. Some researchers wonder whether the belt was stirred so thoroughly during the early migrations of the giant planets that any original order has been scrambled. In that view, a dark asteroid near the inner edge might be a visitor from the outer solar system, flung inward long ago and left stranded. A pale, stony body in the outer belt might have wandered out from closer to the sun. The light still carries a real signature, but the location no longer tells us where the rock was born. The library in this picture has been shaken, and its books have landed on the wrong shelves. There is also the slow weathering that sunlight itself causes. Over millions of years, the steady drip of solar particles and tiny bits of dust can darken and redden the surface of an asteroid. This is called space weathering, and it makes the outermost skin of a rock look different from the fresh material just beneath. So the light we read is not always the truest light. It is filtered through age, like a varnish on an old painting. To see the real colors, scientists sometimes have to imagine what lies under that varnish, or wait for a fresh impact to expose the brighter material below. The deepest mystery is what the original colors mean about the original chemistry. Carbon-rich asteroids may hold complex molecules that formed in the cold outer reaches, the kind of molecules that on Earth became the building blocks of living things. Metallic asteroids may be the broken cores of small worlds that grew warm enough to separate iron from stone before something shattered them. Each color, then, hints at a different story of formation, of heating, of breaking, of survival. And we are still learning to read those stories from the faint light alone. So when you picture the belt tonight, picture it lit only softly, each stone catching a thin sheen of distant sunlight and sending a little back. Picture the colors as quiet rather than bright. A muted gray here, a dusky red there, a glimmer of cold metal turning slowly in the dark. Each tone is a sentence in a language we are still learning. The full meaning has not yet been settled. The belt holds its record patiently, and we read it slowly, one reflected ray at a time, in no particular hurry to finish. Space is silent. That is one of the first things we learn about it. Sound needs a medium to travel through, like air or water, and the gaps between asteroids hold almost nothing at all. A stone the size of a mountain could split open out there, and no ear, no matter how close, would catch a single note. The belt is a place of motion without music, of impacts without echoes, and yet, in a strange and beautiful way, the belt is full of sound. Not sound we could hear with our ears, but sound we can build with our instruments. Every collision out there sends vibrations through the rock itself. Stone is a medium. When two asteroids meet, the shock waves ring through their interiors like a bell struck from the inside. We cannot hear it, but the asteroid, in its own quiet way, sings. Some of those songs travel further than the rock that made them. When a large impact happens in the belt, tiny shards spray outward. Some of these shards drift inward over millions of years and eventually reach Earth as meteorites. Inside those meteorites, scientists find shock veins, thin dark lines where the rock briefly melted under the pressure of an ancient collision. These veins, are the frozen record of a sound that once rang through a now vanished parent body. We are, in a sense, holding the echo in our hands. Spacecraft have given us another way to listen. When a probe flies past an asteroid, it measures faint changes in radio signals, slight wobbles in its own path, subtle pulls of gravity. Researchers can take those measurements and turn them into audio, mapping the data onto frequencies our ears can follow. The result is not the true sound of the asteroid. It is a translation, a way of letting us feel the rhythm of something otherwise hidden from us. The solar wind also plays a role in this quiet music. A steady stream of charged particles flows outward from the sun, washing over every stone in the belt. When this wind strikes an asteroid, it sets up faint electric and magnetic ripples in the space around it. Instruments can record those ripples and shift them into the range of human hearing. What comes out sounds like a soft hiss, sometimes a low whistle, sometimes a slow pulse. It is the belt speaking in a language we had to invent ears for. Then there are the deeper vibrations, the ones we suspect but cannot yet measure directly. Some asteroids appear to be loose piles of rubble, held together by gravity alone. When such a body is nudged by a small impact, the whole pile shifts and resettles. Inside, grains slide against grains, boulders tilt, dust packs into new shapes. The motion is slow and faint, but it is, in essence, an asteroid quake. One question that remains open is how often these quakes happen and how strong they can be. We have only just begun to measure the trembling of small worlds. Larger collisions leave longer echoes. When an asteroid breaks apart, the fragments do not scatter randomly. They keep orbits close to the original path, drifting together as a family for millions or even billions of years. Astronomers can trace these families backward in time, reconstructing the moment of breakup. In a way, every asteroid family is a chord still ringing from a strike that happened long before any human walked the earth. The sound is gone, but the pattern of motion remembers. There is something gentle about this idea. The belt is loud in its own quiet way. It is full of motion and impact and shifting stone. All of it happening in a silence so deep only mathematics and instruments can translate it. Every meteorite we find is a small recording. Every spacecraft flyby is a microphone pressed against a closed door. And the door, slowly, is opening. Some researchers wonder whether future missions might place tiny seismic sensors on the surface of an asteroid, the way we have placed them on Mars and the Moon. If they do, we may finally listen to the inside of a small world. We may learn whether its heart is solid or hollow, packed tight, or full of empty pockets. The question of what the belt truly sounds like from the inside remains open. For now, we listen in translation. We let the data sing for us, and we sit with the strange thought that out there, in the great silent ring between Mars and Jupiter, collisions are still happening, still ringing through stone, still leaving their slow echoes in orbits and fragments, and the small dark veins inside fallen meteorites. The belt is quiet, but it is not still. There is a quiet kind of mathematics at work in the asteroid belt, and it shapes everything we see there. Orbits trace patterns that follow simple rules, written long ago in the language of gravity. A stone the size of a city loops around the sun on a path you could predict for centuries to come. Knowing only its distance and its speed, an astronomer can sketch where it will be on any given night, years from now. The math begins with a rule worked out 400 years ago. The square of the time an object takes to circle the sun is proportional to the cube of its distance. That single line of arithmetic governs every rock in the belt. A small asteroid near the inner edge completes its loop in about 3 of our years. One drifting near the outer edge takes closer to 6. Slow and steady, each one moves at exactly the pace its distance allows. Within that quiet clockwork, smaller patterns appear. Asteroids sometimes pair with one another, locked into ratios so clean they feel almost designed. 2 stones might orbit so that one completes 3 loops in the time the other completes 2. Astronomers call these resonances, and they appear everywhere, in planets, in moons, in dust. The universe seems to prefer simple fractions when it can find them. The math also reveals something stranger. Some asteroids carry their own tiny moons, roughly 1 in 6 larger asteroids, is now thought to have at least one small companion in orbit around it. These pairings were not even confirmed until the 1990s, when a spacecraft glimpsed a small moon called Dactyl circling an asteroid named Ida. Since then, hundreds more have been found. The belt is full of quiet little systems within the larger system. How these tiny moons form is still partly an open question. One idea is that a fast spin slowly throws material off the parent asteroid's equator, and that material gathers into a small companion. Another idea is that gentle collisions chip off a piece, which then settles into a slow orbit nearby. Both processes may happen. Both leave behind elegant geometries, two stones turning around a shared center, sometimes for billions of years. The numbers behind these little dances are surprisingly small. A moon orbiting 100-mile-wide asteroid might circle it once a day, drifting along at the speed of a slow walk. Gravity there is faint, almost gentle. A person could step off the asteroid's surface and float for a long time before coming back down. Yet that faint gravity is enough. Given enough time, even the softest pull writes a closed curve in space. There is a kind of beauty in how predictable it all is. The orbits of the major asteroids have been mapped so carefully that we know where Ceres will be on this date 1,000 years from now, to within a small margin. Vesta's path is charted just as cleanly. The math is not difficult. It is the same arithmetic that guides a stone tossed across a pond, only stretched out over years and across millions of miles. The distances involved help give the belt its quiet character. The average gap between any two asteroids is far larger than people often imagine. If you stood on one and looked toward the next, you would usually see nothing at all but stars. The math of volume tells the story. Spreading a few million stones through a ring, nearly 1 billion miles across leaves almost all of that ring empty. The belt is mostly silence. Light itself becomes part of the arithmetic. A signal from a spacecraft near Ceres takes about 20 minutes to reach Earth at the closest approach, and nearly an hour when the planet is on the other side of the sun. Light years are too large a unit for the belt. Here we measure in light minutes, yet the same rules apply. Every photon obeys the same simple speed, and every orbit obeys the same simple law. What remains unresolved is whether these patterns reveal something deeper. Some researchers wonder if the ratios we see, the resonances, the tidy fractions, the way certain orbits empty out, while others fill in a point to hidden rules we have not yet written down. Others suspect we already have the rules, and we simply need more time and finer measurement to fit every stone into place. The question stays open. For tonight, it is enough to picture the math as music. Each asteroid keeps its own slow beat. Pairs of stones trade quiet counts of 3 against 2, of 5 against 2, of 7 against 3. A few carry tiny moons that turn around them like soft second hands, and the whole arrangement drifts on, simple, predictable, and quietly beautiful in the dark. For most of human history, the asteroid belt was only a smear of faint dots in a telescope. Tiny points of light moving slowly against the stars, too small to show a face or a shape. We could measure their orbits and guess at their sizes, but we could not truly see them. They were rumors of worlds, not worlds themselves. To know a stone, you must visit it, and for a very long time, no one had ever visited. That changed slowly, one quiet mission at a time. A spacecraft would leave Earth, drift for years across the dark, and then pass close to a single asteroid for only a few hours. The encounter would be brief, almost gentle, like a stranger walking past a sleeping animal in the woods. The probe would snap its photographs, gather its measurements, and then drift onward, carrying its small bundle of new knowledge back home across the silence. The first close looks showed us something we had only guessed at. Asteroids are not smooth balls. They are battered, pitted, sometimes shaped like potatoes or peanuts or broken bricks. Some are covered in fine gray dust. Some are stacks of loose rubble held together by the faintest tug of their own gravity. Some have tiny moons of their own, smaller stones drifting in lazy circles around larger ones. Each new visit raised more questions than it answered. A few missions did more than fly past. They slowed down, matched orbits, and stayed. One spacecraft circled the bright asteroid Vesta for over a year, mapping its scarred surface and its enormous southern crater. Then it moved on to Ceres, the round one, and saw bright salty patches glowing on the floors of dark craters. No one had expected that. The bright spots are thought to be salts left behind by water rising from below. But the full story of how they formed is still being pieced together. Other missions went further still. They reached out and touched the stones. A small Japanese probe drifted down to a rough little asteroid, tapped its surface, and lifted a few grains of dust back into space. Another mission did the same at a different small world, gathering a small handful of dark, carbon-rich material. These grains, smaller than sand, traveled back across the solar system in sealed capsules. When scientists opened them on Earth, they found water locked in the minerals and the soft chemistry of carbon and the faint chemical signatures of a time before the planets were finished forming. Each of these missions worked because of an almost absurd balance of small things. The spacecraft had to leave Earth at the right moment, in the right direction, with the right amount of speed. A delay of a few weeks, and the target would no longer be reachable for years. A small error in fuel, and the probe would miss its quiet rendezvous and drift onward into the dark forever. The stones themselves move slowly, but the gaps between them are enormous, and a spacecraft must aim with extraordinary care to find one specific rock among millions. Even the act of touching an asteroid is a delicate problem. Many of these little worlds have almost no gravity. A spacecraft cannot land on them in the usual sense. It must hover, drift in, tap lightly, and pull away before the encounter becomes a collision. Push too hard, and you bounce off into space. Push too softly, and you gather nothing. The engineers who planned these visits had to think about a kind of physics that almost never matters on Earth, where everything is heavy and everything stays put. What we have learned from these gentle touches is real, but it is also a tiny sample. We have visited only a handful of asteroids out of the many millions in the belt. Each one we have seen is different from the others in ways we did not predict. Some are dry and stony. Some are rich in water and carbon. Some are loose piles. Some are solid chunks. The belt, it seems, is not one thing. It is a quiet museum of countless small histories, and we have read only a few of its pages. The deeper question remains open. We do not yet know how typical any of our visited asteroids really are. The ones easy to reach may not represent the belt as a whole. The strange ones may be more common than we think. Until we visit far more of them, the picture stays incomplete. The stones we have touched have told us much, and yet they also remind us how much of the belt has never felt the careful brush of a human-made machine. Among all the questions the asteroid belt holds, one quietly stands above the rest. It is a question about us, about how we came to be here at all. The puzzle goes like this. Our planet, when it was young, was a place of molten rock and harsh heat. Yet today it holds oceans, rivers, clouds, and living things. Where did the water come from? Where did the carbon, the building block of life, first arrive? And could the answer lie out there, in the slow drift of stones between Mars and Jupiter? Some researchers wonder if asteroids carried the seeds of Earth's living chemistry across the empty miles. Many of the rocks in the outer belt are dark and rich in carbon. They hold tiny amounts of water locked into their minerals. They hold simple molecules that on Earth are part of every living cell. If billions of such stones rained down on the young Earth, they could have delivered both the water and the chemistry that life would later use. This idea is gentle and tempting. It places the cradle of our beginnings somewhere out beyond the reach of our eyes. But the question is not settled. Other researchers point to comets, the icy travelers from far past Neptune, as another possible source of Earth's water. Still others suggest the water was here from the start, baked into the planet's rocks as it formed, slowly released over long ages. The truth may be a blend of all three. The belt may have brought one piece, the comets another, the young Earth itself a third. We do not yet know the recipe. Clues come from a careful kind of measurement. Water is made of hydrogen and oxygen. Hydrogen comes in two slightly different forms, one a bit heavier than the other. Each source of water in the solar system carries its own ratio of these two forms, like a quiet fingerprint. When scientists compare Earth's oceans to the water locked in certain meteorites, the fingerprints sometimes match closely. When they compare Earth's oceans to some comets, the fingerprints are different. This hints that much of our water may have come from rocky bodies in the outer belt, not from icy comets. But the sample is small. Many comets have not been measured. Many asteroids have not been sampled. The picture is sketched only in faint lines. The molecules of life add their own layer of mystery. In certain dark, carbon-rich meteorites, scientists have found amino acids, the small parts that make up proteins. They have found sugars and the chemical letters that, in a different order, spell out the code of every living thing. These molecules formed in space long before any planet warmed beneath any sun. They formed in the cold parent bodies of asteroids, where water and carbon and a little heat could mix in slow, patient ways. Whether those molecules ever did the work of starting life on Earth, no one can say with certainty. They may have been raw ingredients. They may have been only one ingredient among many. The question remains open. There is a quieter wonder hidden inside this puzzle. If the asteroid belt seeded Earth with water and carbon, then it may have done the same for other worlds. Mars, in its youth, had rivers and lakes. Venus, before it became a furnace, may have held oceans. The same dark stones that fell on Earth fell on them too. What grew there, if anything, we still do not know. Future missions may bring back small grains from carbon-rich asteroids, sealed and untouched, for slow study in clean laboratories. Each grain is a tiny letter from the deep past. Each may carry a few more words of the story. For now, the belt sits in its long orbit, holding its quiet secret. It is possible that life on Earth began entirely from materials that were always here. It is possible that without the slow rain of asteroids, our world would have stayed a dry and silent stone. It is possible the truth lies in some shape we have not yet guessed. The evidence is incomplete. The instruments are still being built. The samples are still being gathered, one careful gram at a time. It is a soft thought to rest with, that somewhere in the dark, between Mars and Jupiter, drifting among rocks may still be the answer to where our oceans came from. That the water in a glass on a bedside table may have begun its long story out there in the cold, billions of years before there was anyone to drink it. We do not know yet, and the not knowing tonight is a kind of gift. So we come to the question of time, not the small kind measured in days or years, but the deep kind measured in millions and billions. What will the asteroid belt look like in a future so distant that our own world will have changed beyond recognition? The honest answer is that we do not know. We can sketch a few possibilities, each shaped by the slow forces that have been at work since the belt first formed. But the details remain open, and the further out we look, the more uncertain the picture becomes. One thing seems likely. The belt is slowly losing mass. It has been losing mass for billions of years. Every collision sends fragments tumbling into new paths. Some of those paths cross the orbit of Mars or Earth, or fall inward toward the Sun. Others drift outward and are gently nudged away by Jupiter. Over very long stretches of time, the belt becomes a little thinner, a little quieter, a little less crowded with stone. If this slow leak continues, the belt of the far future may be a faint shadow of what we see today, but the rate of that loss is one of the open questions. Some models suggest the belt has already lost more than 99% of its original mass during the chaos of the early solar system. If most of the leaving happened long ago, then what remains today may be relatively stable, drifting along for billions of years with only gradual changes. Other models suggest the slow grinding will continue at a steady pace, reducing the belt piece by piece until very little is left. We cannot yet say which picture is closer to the truth. There is also the matter of the sun itself. Our star is middle-aged, calm, and patient, but it will not stay that way forever. In roughly 5 billion years, the sun is expected to swell into a red giant, a vast glowing sphere that will reach out far past the orbit of the Earth. What happens to the belt during that long expansion is another open question. Some of the smaller, darker bodies may be heated until their ices vanish into space. Some may be pushed outward as the sun loses mass and its gravitational pull weakens. Others may simply continue on their slow orbits, bathed in a redder, gentler light. In the time before that great change, smaller shifts will keep reshaping the belt. Jupiter will continue its quiet influence, tugging on certain orbits and clearing certain gaps. Collisions will keep happening, though more rarely as the population thins. New families of fragments may appear, each tracing its origin back to some long ago shattering. The belt is not a finished object. It is a slow, ongoing process. And that process has no clear endpoint that we can see. There are stranger possibilities too, and they remain firmly in the realm of speculation. One idea is that, far in the future, intelligent life might mine the belt for metals and water, gradually rearranging its contents. Another idea is that the belt might be disturbed by some passing star, its orbits scattered into new and unfamiliar patterns. Neither of these is predicted by any settled theory. They are simply reminders that the future is open and that the belt's quiet present is not a guarantee of a quiet tomorrow. If we step back even further, we can imagine the very long future of the solar system itself. After the sun's red giant phase, it is expected to shrink into a small, dense white dwarf, glowing faintly and cooling slowly over enormous spans of time. The remaining planets and asteroids would continue to orbit this dim ember. The belt, or what is left of it, might still be there, drifting in the cold and the dark, lit only by the pale light of a dying star. What it would look like in that distant age, and how much of it would survive, remain questions we can only wonder about. It is humbling to think that the stones we study today have already outlived countless generations of stars elsewhere in the galaxy. They were here before the first life appeared on Earth. They will likely still be here in some form long after the last human story has been told. The belt belongs to a timescale that dwarfs our own, and yet it is not unchanging. It is becoming something, slowly, constantly, and we are watching only the briefest sliver of that becoming. What the belt will be in 1,000,000 years, or 1,000,000,000, or 10 billion, we cannot say with certainty. We can only watch and measure and listen and let the long quiet work itself out in in the dark spaces between the worlds. Step back now, all the way back, until our own sun is just one quiet point of light among billions. The asteroid belt we have been wandering through is small in the grand view. A thin ring of rubble around a single star, in one arm of one galaxy, in a universe that holds more galaxies than grains of sand on every beach on Earth. And yet, as far as we can tell, our belt is not alone. When astronomers point their telescopes at other stars, they often see faint glows of dust and rock circling them. These are called debris disks, and many of them look very much like our own belt, only larger and brighter. Some surround young stars still in the process of forming planets. Others surround older stars, stars that have already finished building their worlds. The dust catches starlight and warms slightly, giving off a soft infrared glow that our instruments can detect from light years away. One of the most famous of these glowing rings circles the bright star Vega. Another wraps around Fomalhaut with a sharp inner edge that suggests an unseen planet shaping it like a shepherd. There are hundreds of such systems now. Each one is a hint that the story we have been telling tonight, a young star, a swirl of dust, planets gathering and bullying, rocks left over in the gaps, may be a common story across the galaxy. But here the open questions return. We cannot yet see the individual asteroids in these distant belts. They are far too small. We only see the collective glow of the dust they shed when they crash into one another. So we are guessing at their shapes, their sizes, their compositions. Some researchers think a few of these systems may hold belts very similar to ours. Others suspect many are far more chaotic, with rocks the size of small moons grinding against each other in slow violence. The truth, for now, sits just beyond our reach. There is something gentle in this thought. If belts of stone are common, then the leftovers of planet building are common too. Every star with worlds may also have its own quiet archive of beginnings, its own small library of frozen rubble, holding the chemistry of that system's first days. Somewhere out there, perhaps, another belt is being studied by another patient mind, wondering about its own unanswered questions. The atoms in those distant asteroids and the atoms in our own are likely cousins. They came from the same kinds of sources. Hydrogen forged in the first moments after the universe began. Heavier elements built inside ancient stars, then scattered when those stars died in long, slow shedding or in sudden bright collapse. Carbon, oxygen, iron, silicon, calcium, all of it cooked in stellar cores. All of it spilled into the dark. All of it gathered again into new clouds, new stars, new belts. The calcium in your bones, the iron in your blood, the oxygen filling your lungs as you breathe slowly towards sleep. These atoms once drifted through interstellar space. Some of them likely spent time inside asteroids before Earth gathered them up. The stones in our belt and the stones in your body share an ancestry. You are, in a small but very real sense, made of the same material as the quiet rubble circling between Mars and Jupiter. This is not poetry. It is plain chemistry, and it means the asteroid belt is not some far away curiosity. It is a relative, a sibling left over from the same nursery that built the earth, that built the water in your glass, that built you. What remains open is whether the patterns we see here repeat everywhere. Do most stars keep a belt of leftovers? Do some lose theirs entirely, swept clean by wandering planets? Do some hold many belts, nested like rings? We do not yet know. Each new telescope brings the answer a little closer, and each answer seems to bring 3 more questions with it. For now, picture it this way: a galaxy filled with quiet stars. Around many of them, soft rings of dust and stone, glowing faintly in the cold. Each ring a slow record of how worlds came to be. Each ring a little like ours. And in one of those rings, on the third small world from one ordinary star, a listener lies in a warm bed, drifting toward sleep, made of the same atoms as everything else, sharing a long and patient kinship with the stones. The universe is enormous. The belt is small, and the connection between them and you is real and old and still mostly unknown. And so we come to the quiet end of our long, slow walk through the belt. We have wandered among broken stones and round little worlds. We have sat with old questions and gentle theories. We have looked at carbon and ice, at at metal and dust, at the soft glow of sunlight on ancient rubble. None of it has been fully solved. That is part of why it is so beautiful. Picture the belt now, one last time, in your mind. A wide, soft ring between Mars and Jupiter. Not crowded, not dangerous. Mostly empty space, with small dark shapes turning slowly in the cold. Each stone moves at its own quiet pace, on its own long orbit, drawing patient circles around the sun. Some are round and shy. Some are jagged and tumbling. Most are too small to see, even with a strong telescope. They drift in silence, and they have drifted in silence for billions of years. The sun from out there looks small, brighter than any star, yet far away. Its light is pale and thin. It touches the gray surfaces gently, warms them by a few degrees, and then moves on. Long shadows stretch across cratered ground. Tiny grains of dust hang above the surface, lifted by static, settling again over centuries. Nothing rushes, nothing crashes tonight. The belt is mostly resting. We still do not know exactly how it came to be. One idea says Jupiter stirred the early disk and stopped a planet from forming. Another idea says the belt is a quiet meeting place where pieces from many parts of the young solar system drifted in and stayed. Both stories may be partly true. Both leave room for more questions. We do not yet know how much water the belt holds, or how often its rocks have nudged life on Earth, or what shape it will take 1 billion years from now. The mystery is still open, and that is a kind of gift. Let the picture soften now. Imagine yourself drifting above that wide ring, weightless and warm. The stones turn below you. Ceres glows faintly, round and patient. Vesta shines a little brighter, pale as old bone. Pallas tilts off to one side, taking its own strange path. Far beyond them, Jupiter rolls in slow bands of cream and rust, with its small swarm of Trojans keeping pace. Farther still, the outer planets drift in deep blue silence. And beyond all of that, the stars. There are so many stars, quiet ones, old ones, young ones still wrapped in the dust that made them. Around many of them, other belts are turning, other rings of stone and ice, holding their own unfinished stories. The universe is full of these soft, slow places. Most of it is gentle. Most of it is waiting. Most of it will never be touched by anything but light. You are small here, and that is a comfort. The belt does not need you to understand it. The galaxy does not need you to solve it tonight. The questions will still be there in the morning, patient as the stones themselves. Researchers will keep looking. Spacecraft will keep listening. New telescopes will open new windows, and old ideas will be gently set aside for better ones. The mystery will move forward without you for a while. You are allowed to rest. Feel the weight of your body settle. Feel the quiet of the room around you. Far above, the real sky is turning, slow and steady, the way it has turned for every night of every life that has ever been lived. Somewhere out there, a small gray asteroid is catching the sun for the first time in 1,000 years. Somewhere out there, a grain of dust is drifting from one orbit to another, carrying a story no one will ever read. The universe keeps its quiet work going while you sleep. We may learn more about the belt in our lifetime. We may learn how it formed, what it carries, where its pieces have traveled. Or we may not. Some answers will come slowly over many human lives, passed from one curious mind to the next. For tonight, the not knowing is enough. For tonight, it is enough to picture that soft ring of stones turning in the dark, holding its secrets gently. You can let your thoughts drift out there among them, and you can let them go. Rest now. The stones will keep turning. The sun will keep shining. The questions will keep waiting kindly for whenever you wish to return. Subscribe for a brand new space topic every night. One tap and something incredible is waiting for you tomorrow. Sweet dreams.